In this example, we will find a power series solution to a differential equation. So let's find the power series expansion about x equals 0 for a general solution to the given equation, y prime plus 2xy equals 0. So we start by assuming that the solution is a power series about x equals 0. So it has this general form. Sum of a sub n times x to the n with n from 0 to infinity. So let's take the first derivative and substitute into our equation. The first derivative is the derivative of a0, 0, plus the derivative of a1 times x, which is a1, plus the derivative of a2x squared, which is 2 times a2 times x, plus the derivative of a3 times x cubed, which is 3 times a3 times x squared, plus dot dot dot. So we write this as a sum as n goes from 1 to infinity of n times a sub n times x to the n minus 1. That's like taking the derivative of a n times x to the n with power rule and writing it n times a n times x to the n minus 1. But this series starts at n equals 1 because n equals 1 here will give us 1 times a1 times x to the 0, and x to the 0 is 1. So the first term is a1, and the first derivative starts with this term a1. So just remember this one starts with n equal 1. So substitute y prime and y into the equation, and we get this equation. That's y prime plus 2xy. Now we multiply by 2x inside the sum. So the first sum is copied, and the second sum is written as sum as n goes from 0 to infinity of 2an times x to the n plus 1. Again, 2x times an times x to the n is 2an times x to the n plus 1. So this is equal to 0. Now we have this equation, and we need to write the sum of these two series as one series, one single summation. In order to do this, these two series should have the same general term x to the power k. So instead of x to the n minus 1 for the first series, we want x to the k. So we shift the index, we let k equal to n minus 1. Solve for n, we get n equals k plus 1. The first series starts with n equal 1. When n equals 1, k is 1 minus 1, which is 0. So the first summation, which is sum of n times an times x to the n minus 1, with n from 1 to infinity, will be written in this form by using n equals k plus 1, sum of k plus 1 times a sub k plus 1 times x to the power k, where k goes from 0 to infinity. It starts with k equals 0. Alright, now for the second summation, we want this general term to be x to the power k, so we will let k to be n plus 1. So to shift the index for the second summation, we let k to be n plus 1. We solve for n equals k minus 1. And the second series starts at n equals 0. If n equals 0, k would be 0 plus 1, which is 1. So the second summation, which is sum of 2 times an times x to the n plus 1, where n goes from 0 to infinity, can be written in this form. Sum of 2 times a sub k minus 1 times x to the power k, where k goes from 1 to infinity. We substituted n equals k minus 1. So substituting the first summation and the second summation into our equation, we obtain this equation 2 here. That's the first summation, and that's the second summation. Alright. Now, both of these summations have the same general term, x to the power k. But notice that the second summation starts at k equals 1 and the first summation starts at k equals 0. We would like both of these to start at k equals 1. So we'll have to rewrite the first summation. Sum of k plus 1 times ak plus 1 times x to the k, where k goes from 0 to infinity. We will write the first term of this series separately. To see what is the first term of this series, we make k equals 0. 0 plus 1, 1, times a sub 1 times x to the power 0. Remember, x to the 0 is 1. So the first term of this series, obtained by making k equals 0, is a sub 1. Plus the remainder of the series, sum as k goes from 1 to infinity of k plus 1 times ak plus 1 times x to the power k. So substituting this for this in the second equation, we obtain a1 plus sum as k goes from 1 to infinity of k plus 1 times ak plus 1 times x to the power k plus 2 times ak minus 1 times x to the k, where k goes from 1 to infinity equals 0. We will have to combine these two summations and write just one summation. We can do this because both of these start at the same value of k equals 1, and both of these have the same general term x to the power k. So we write the first term, a sub 1. And now here we factor x to the power k. So we get sum as k goes from 1 to infinity. And by factoring x to the power k, we get x to the k times ak plus 1 times k plus 1, that's this term, plus 2 times ak minus 1, that's this term over here. So this equals to 0 for all x. A power series is equal to 0 for all x when all the coefficients are 0. So we will have to set all of the coefficients to 0. The first coefficient is a sub 1 equals 0. And the other coefficients are obtained from this series by looking at what we have in this bracket. So we get k plus 1 times a sub k plus 1 plus 2 times ak minus 1 equals 0. For k greater than or equal to 1, because this summation starts at k equals 1. So we will need to use the recurrence relation and find the coefficient with the biggest index. Find a sub k plus 1. So a sub k plus 1 will be negative 2 times a sub k minus 1 over k plus 1, which we write negative 2 over k plus 1 times ak minus 1 for k greater than or equal to 1. So we will choose some values of k and find different coefficients. But remember that a1 was the first coefficient, which was 0. So by making k equals 1, we get a2 equals minus 2 over 1 plus 1, so over 2 times a0, minus a0. We don't know a0, so we just leave the equation in this form. A sub 2 equals negative a0. When k equals 2, we get a3 equals negative 2/3 times a1. a1 is 0, so we get 0. Now we make k equals 3. We get a4 equal negative 2 over 4 times a2. a2 is negative a0, so we substitute, we get 1/2 a0. Now we make k equals 4. We get a5 equals negative 2 over 5 times a3. And a3 is 0, so we get a5 equals 0. Now we make k equals 5. We get a6 equals negative 2 over 6 times A4. A4 is 1/2 A0, so substituting that we get negative 1/6 times A0. And 6 is equal to 3 factorial, so we'll write it in this form. We get negative 1 over 3 factorial times A0. Remember, 3 factorial is 3 times 2 times 1, which is 6. Now, k equals 6 gives us A7 equal negative 2 over 7 times A5. A5 is 0, so A7 will be 0. Let's use k equals 7. We get A sub 8 equals negative 2 over 8 times A6. A6 is negative 1/6 times A0, so we get 1 over 24 times A0. And 24 is 4 factorial because 4 factorial is 4 times 3 times 2 times 1. 4 times 6, 24. So 1 over 4 factorial times A0. And if we use k equals 8, we get A9 equals negative 2 over 9 times A7. A7 is 0, so A9 will be 0. So we are trying to figure out a pattern. Over here, all the coefficients with the odd index are equal to 0. So A sub 2n plus 1 will be 0. Over here, the coefficients with even index, notice that they have the sign negative, positive, negative, positive. So that accounts to this minus 1 to the power n here. Over n factorial, notice here we have 2, which is the half of 4, 3, which is the half of 6, 4, which is the half of 8. So over n factorial times A0. Again, to check, let's make n equals 1. If n is 1, this formula would tell us that A sub 2 is minus 1 to the first power. So minus 1 over 1 factorial. So minus 1 over 1, which is minus 1 times A sub 0, which is this. So we get this general formula, A sub 2n equals negative 1 to the power n over n factorial times A0. And for these coefficients with odd index being all equal to 0, we get A sub 2n plus 1 equals 0. When n equals 0, this means A sub 1 equals 0. When n equals 1, this will give us A sub 3 equals 0. When n equals 2, this gives us A sub 5 equals 0, and so on. So now we substitute into the solution A0 plus A1x plus A2x squared, and so on. Remember that A1 is 0, A3 is 0, so we will get no odd powers here. All we get is A0 minus A0 times x squared, because A2 is negative A0, plus 1 over 2 factorial times x to the 4th, because A4 is 1 over 2 factorials times A0, plus dot dot dot. Factor A sub 0, we get A0 times parenthesis 1 minus x squared plus 1 over 2 factorial times x to the 4th plus dot dot dot. So we get A sub 0 times the summation, sum as n goes from 0 to infinity of minus 1 to the power n over n factorial times x to the 2n. We use the formula for A sub 2n here, times x to the 2n, because we only had even power. So we'll just make a quick remark that this power series here can be written in this form, sum of 1 over n factorial times negative x squared to the power n, which is e to the negative x squared, because this is the summation for e to the x. So the solution can be written as y of x equals A sub 0 times e to the negative x squared. We don't have to do all of this if we just get this